Disturbances and incidents happen regularly in refinery utility centers. Operators are key in managing these and preventing that a disturbance becomes a big hit incident. What I experienced as a utilities technologist in the last 35 years is that many big hit incidents could have been prevented if operators and technologists would have been aware of the threats. And of course would regularly have discussed them. There were several actions that could have been taken to prevent the outcome, a total refinery shutdown, even after the first alarms arrived in the control room. This video is set up for use as a 1-hour break during the night shift, in which you as a team will discuss the questions raised. When the questions are on the screen, you pause the video and start discussing what would be applicable for your boiler house. Once you're ready, compare your thoughts with mine by starting the video again. If you discover that there is a serious threat that needs addressing, please contact your management and propose ways to reduce the risk. This video is set up with this arrangement in mind. Some calculations are done with 70 bar steam. The general conclusions, however, apply for a much wider range of pressures, let's say 10 to 120 bars. Steam boilers are quite standard these days. For this picture, it is relevant that the boiler has a steam drum for separating steam and water, that there is a superheater, possibly with injection water for temperature control. In the systems just shown, what could possibly go wrong? Particularly the incidents that bring the refinery down are the ones I'm after here. Please note all your thoughts about risks around your boiler house. Now, please stop the video and start writing. Once you're ready, please start the video again. When you give me 4 minutes, I may not have all the answers on this slide either, but it is good to think about all the things that go generally well because of well-designed and well-maintained equipment. Operators intervening when disturbances occur. That's also an important fact that avoids problems. In this video, we'll focus on the yellow highlighted subjects. I've come across a few incidents where at the startup of a boiler, either the water level in the drum was too high or the startup was much too fast. When steam production starts in the evaporator tubes, the steam bubbles push water to the steam drum. If this happens too fast, the water in the steam drum increases even further and may first affect the efficiency of the separator devices and then reach the superheater as a slug of water. This slug eventually reaches the steam distribution system. Don't think that this water will simply mix with the steam already in the system. As I've seen in a European refinery, the slug of water may stay at the bottom of a steam header, and once the steam flow really picks up, suddenly the slug will start to move at up to 40 meters per second, that is the steam velocity, and hit the steam turbine with devastating effect. Occasionally, a steam line has to be brought online after a maintenance activity or something like that. The heating up of the steam line may come from the superheat of the steam or from condensation of the steam. The condensation inevitably happens when the steam line is still below the saturation temperature of the high pressure steam. In our 70 bar steam system, this means that while the steam line is still below 286 degrees Celsius, steam will condense against the wall. This water should be removed from the steam line via a removal system. This could be with steam traps or with manual valves that ensure that the water is removed from the steam line. If, however, too much water remains in the line, this could have three different devastating effects. Firstly, when the steam line starts to flow in surface, a slug of water could damage a nearby steam turbine. By the way, this is one of the reasons why a steam turbine is usually connected to the top of a main distribution steam line. This way, the risk of water hitting the steam turbine is significantly reduced. If cold water is left in a steam line while the steam pressure increases, the water could stay cold, except for a small surface layer. The top of the steam line, however, heats up quickly because of the condensation of the steam on the wall. The top part of the line will therefore expand. The end result of this is erratic and potentially violent movement of the steam line on its supports. I know of a case where a steam line nearly hit an office of the manager of the boiler house. On this picture it is visible how much movement of steam lines is possible as a result of water in steam lines. There are enough examples where the steam line failed as a result of the violent movements. Take a closer look at the supports of the two steam lines and the cracks in the concrete beam. But possibly the most surprising effect that could result from cold water in a steam line is an explosion. Such an explosion is caused by implosions of steam bubbles in the cold water. Compare it to the noise when in a coffee bar the steam enters the milk for making cappuccino. When the milk is cold, the noise can be very strong. This is the sound of imploding steam bubbles. Imagine that in a steam line this effect can be much stronger. In this picture you can see the devastating effect of what they call condensation-induced water hammer. We look at a hole in an 18-inch or 450 mm diameter 14-bar steam line. Part of the plant was out of operation until the steam line was repaired. The water in this steam line was there because of not functioning steam traps in a road underpath. Let's visualize what happens in this type of water hammer. When steam starts to flow, it will create waves on the surface of the cold condensate in the line. Once the wave is high enough, it creates a liquid seal in the steam line. Due to the movement of the water behind the plug, condensation of the steam continues. Due to the vacuum behind the seal, the plug of water accelerates, until the water collapses on itself and creates a strong pressure wave. You may have heard this type of noise in your refinery before. In too many locations, steam lines have exploded as a result of condensation-induced water hammer. It can be devastating in HP steam lines. Now back to the boilers. Please think about what you can do to prevent water carryover from the boiler into the steam distribution system. Most of the things mentioned in the next slides you're probably already doing, but it is good to think them all through. Now please stop the video and start writing. Once you're ready, please start the video again. Start with the procedures. That's obvious. What do they state? What experience at your site has led to updates on the procedures? Have events around startups of the boilers been logged so you can have a closer look whether they work with respect to the water level? My take on it is as follows. If each time that you fire up a boiler a high level alarm goes off, you may want to revise your procedures. One of the possibilities here is to aim for a lower initial level in the drum before you really fire up the boiler. If, however, the level stays steady as a rock throughout the startup, have a closer look whether you're happy with the time it takes to start up the boiler, or whether tests can be scheduled to do it somewhat faster. By the way, several boilers have a limitation on the speed to move from minimum stop firing to full load, based on expected fluctuations in the steam drum level. Check these facts for yourself. How does the drum level move when you fire up the boiler? And of course, is the level control scheme handling it very well? Please discuss your findings with the utilities technologist or engineer if you have concerns about this. Calibration of the drum level measurement may be completely sorted out at your boiler house because of the type of level measurement selected. However, in a minute we'll elaborate on this subject a little further. The final proof that there is no water leaving the steam drum with the steam is the temperature of the steam just upstream of the attemperator valve in the superheater, or even the position of the attemperator control valve itself. If there's over the years never an unexplainable deviation from normal valve positions and temperatures, this will be a good sign. Let's have a closer look at the boiler drum and what to expect of it. In most high pressure boilers, there are at least two sets of internals present, cyclones and demisters. For them to work properly, the water level should normally be around the, well, you expected that, normal water level mark. But be careful. If it's really designed like that, the side glass should be insulated. In this slide it is shown that if the water in the side glass is almost 60 degrees C colder than saturation temperature, the real level in the drum is significantly higher than indicated by the side glass. Have a check how that's arranged at your boiler drums. If the side glasses are not very well insulated, there is the risk of flooding the cyclones. This can be made worse by the dynamic movement of the drum level. A sudden pressure drop in the steam header will cause additional increase of the steam drum level. Please have a look at this problem and pause the video until you thought about this issue. Because of the flashing of the water in the drum and in the evaporator, the level in the steam drum goes up. In the side glass, only the effect of the extra water being pushed out of the evaporator will be visible. The champagne effect in the drum will reduce the density of the water temporarily and should not lead to a higher side glass level in itself. If the side glass is very properly insulated, then there will be a champagne effect there as well. But subcooled water will not form steam bubbles under those circumstances. I've worked at a European refinery where this effect on the steam drum was much larger than originally anticipated, and frequently the boiler tripped on high drum level. The remedy was to install a back pressure control valve on the superheated steam to the distribution system that kept the pressure in the steam drum constant. I would like to suggest that the next time you see significant pressure fluctuations in your steam distribution system, you check how the level in the steam drum behaves. This will tell you whether you're close to high level trips in your steam drum and therefore close to problems. Discuss with your technologist or engineer if you see potential problems in this area. Please check what type of level measurement is applied in your steam drum. Hydro steps are normally fitted equivalent to the side glass on a steam drum and behave as side glasses. In the picture here you see a radar type of level measurement, which behaves like a side glass as well. The differential pressure measurement will not show changes in density of the water due to flashing, so under dynamic circumstances could give a slightly too low indication of the true boiler drum level. Keep that in mind. In this picture you see some considerations about the various level alarms on your steam drum. Make sure that you know how it's done at your site. You can do a couple of things around water in the steam lines at the heating up of the line. Check on the isometric drawings that there is a fall in the steam line in the direction of the steam flow during startup. Of course, every low point has to have draining facilities. But do they work properly? In this case, reliability of the system is much more important than energy saving. So make sure that the water gets out, if necessary, by opening manual drain valves on the line. Do not leave water in the steam line. The way the water is removed from the steam line requires some extra attention. If the dewatering is like in the picture above, then you have to be very careful with the steam line. In an incident investigation I participated in, a slug of water continued to exist in a steam line, even when the steam to the turbine downstream was already at normal superheated temperatures. When the steam flow increased, finally the slug started to move and damaged the steam turbine. Check your system for insufficient dewatering. If the condensate is roughly at the temperature of the steam, there may not be the risk of condensation-induced water hammer. But certainly slugs can do a lot of damage as well. Now a different problem that I've come across in several refineries. Please note that in these refineries the boiler feedwater pumps all pumped into a common header, from which several boilers took their feedwater. I've dealt with a refinery with some 9 boiler feedwater pumps. Because of the age of the pumps and due to the way the priorities of repairing the pumps, quite often there were weeks in which only 7 pumps were available and running. If, however, one more pump would trip, then there would be insufficient boiler feedwater to continue this operation. Now stop this video and think what you would do in such a situation. Take your time. Discuss this with your colleagues when possible. Please note, you only have a few minutes to decide in the real world. And now you have some time to discuss it in full, what would happen in this case. Hopefully, you came to the same conclusion. You have to reduce steam consumption so much that the remaining 6 boiler feedwater pumps can provide all the water. Theoretically, there could be cases where the spillback valves on the pumps would be passing boiler feedwater back to the deaerator, and it makes sense to close these ones as well. if it is safe enough to do so and if allowed by your systems. Even lowering the steam drum pressure by dropping the pressure in the distribution system could help to get the individual boiler feedwater pumps to a higher flow because of their pump curve. If you would have the exact pump curves of your pumps taken the current condition into account, this would make sense. But usually there's too much uncertainty around this. Therefore, try to reduce steam demand directly. The condensing turbine that is controlled from the boiler house panel makes sense if you have one. But possibly load shedding of a steam consuming plant has to take place. Don't wait too long with this load shedding. Please note that this list of preparations to reduce the impact of a boiler feedwater pump trip is repeated below the video for your reference. A too low steam temperature from the boilers is a tricky one. There's usually not an alarm linked to it. Make sure that you are on top of it, because something has to be done to correct it. Long-term damage can be done to condensing steam turbines, as the increased wetness in the last stages of the turbine will give erosion or wear on the blading. In the enthalpy-entropy diagram, or Mollier diagram, it is visualized what will happen in a condensing steam turbine when the steam temperature will become too low. The 90% line in the diagram symbolizes the minimum quality steam the turbine should be able to consume. This means that 10% of the steam has already been converted to water droplets, and it's these water droplets that do a lot of damage to the steam turbine. Please pause the video and think about the possible causes of a too low steam temperature from a boiler. In what kind of time frame does it need to be solved? Have a look at this slide. Pause if necessary. It may be the result of 1. Injection water control valve erosion. What I came across is a boiler that did have the full boiler feedwater pressure at one side of the control valve and no pressure at the other side. That happened during startup of the boiler, when the steam pressure was 0. Small scratches on the seat surface will quickly result in more erosion and eventually significant passing of the valve. One clear sign that something is wrong with this valve is if the temperature control loop functions well at higher throughputs of the boiler, but starts to fail at low throughputs, because even at minimum stop the valve will pass too much water. 2. Problematic steam drum internals should be prevented by good design, but also by careful checks when the cyclones etc. are installed again after a turnaround. I've come across cases where the inspection department didn't have proper inspection of the internals on their action list. In cases where the inspection was very effective, it was a utilities engineer or technologist who inspected the internals. Make sure this is arranged correctly in the next turnaround of a boiler. 3. Steam drum level measurement has been dealt with before. 4. Foaming is a problem I came across quite recently. Oil entered the boiler via oil contaminated condensate, returning to the boiler house, and various barriers were failing. Internal fouling of the superheater is usually caused by carryover of salts by one of the problems on this slide. I hope you enjoyed this video. Don't hesitate to either connect with me via the email address provided below or comment to this video in the reactions section. If you want more of this, I can tailor a video training via Zoom or Teams with you, or I can provide links to similar training sessions set up with the same methodology. Stay safe.